The Texas hill country has been shaped by the underlying carbonate rocks that we have all over the place. We have faults, we have hills, we have mountains, we have great developments in the topography of the Texas hill country. It's almost sunset and I'm now pointing to Friday Mountain. Friday Mountain is a fault that goes all the way to Mount Bonnell. And like that, we have many features here in the Texas hill country that are due to the underlying carbonate formations. All of these landscape is the product of carbonate rocks. So today we have a lecture centered about carbonates. It's the second part of the trilogy, of the carbonate trilogy. I hope you enjoy it as we can watch the beautiful sunset atop Friday Mountain. Take care and we'll see you soon. Bye. Carbonate formations are the basis of the Texas hill country. Many Texas aquifers find their base in formations such as the Edwards Group, the Trinity Group, all of them outcropping at different places here in Texas. The interesting thing about carbonates is that their pore structure, their storage and flow properties are extremely variable. The carbonate rocks that we have here in the Texas hill country were deposited more or less 100 million years ago. And they were formed by the precipitation of calcium carbonate at sea. There was no mixing with clastic rocks. Yet, if we look at closely at these rocks, we can see cycles. This is what geologists call sequence stratigraphy. There are many cycles, boundaries that coincide with the presence or not presence of certain organisms, fossils. And the presence or not presence of these organisms or variable of composition causes differential dissolution over time. And the differential dissolution over time can be seen in some of these outgroups as the presence of vogs, porosity. We can actually see bioturbation. The holes that we see in some of these rocks that make the rock to be porous and permeable are by and large caused by differential dissolution, the passage of fluids in turn causes precipitation, and also it causes reactions with the host minerals, so that we have the formation of new minerals. We have the recrystallization of minerals. All of that is going to affect the texture, the fabric of the pores. And because of this, some of the rocks are going to be permeable, some of the rocks are not going to be permeable. So it's very important to understand which cycles have which composition, original fossils, and how they become porous and permeable over time because of differential dissolution. Also, the properties of these carbonates can vary in terms of their elastic and mechanical properties. Extremely variable in many ways, in many regards, based on their composition. It's actually very interesting. Most of these rocks are extremely rigid compared to the rigidity that we see in clastic rocks. Here's another interesting outcrop of the Edwards group in the Texas Hill Country. We're looking actually at the side of the fault, and very interestingly, the cycles of carbonate rocks that we see here in this sequence right here in this outcrop, they are all impermeable. If you look carefully, you're going to see that the carbonates here are extremely tight, impermeable, which doesn't happen in other sections of the same Edwards group. And why so? Well, because the constitution of the rock, the initial constitution of the rock, with or without presence of fossils, did not favor the differential dissolution in this area. So when you look at the gamma ray logs of these formation going, if you have a well going through this, you will see that the gamma ray log is flat as a pancake and very low values, exhibits very low values. The resistivity log will show extremely high values on meters just because there's no porosity here, almost infinite values of resistivity. The density log will show very high values of density, which means no porosity. And the sonic log will indicate that this segment of the rock is extremely rigid. The time of flight of sonic acoustic waves will be very short because the rock is very rigid. Here's another view of the Upper Glenrose Formation. Very thick cycle, that carbonate sedimentary cycle that serves as pressure seal for the aquifers that we have in this zone. Some places we can also see fractures in this rock. It's an extremely rigid rock with low porosity. In some of these rocks we see very interesting transitions between very impermeable rocks and permeable rocks. And these transitions are due to the cycles of deposition and the subsequent diagenesis due to pressure and temperature, whereby there's differential dissolution, and the differential dissolution causes the aperture of pores, the circulation of fluids, and the circulation of fluids in turn causes precipitation, recrystallization, also activation of chemical dissolution mechanisms between the fluids because of the action of the fluids on the solids, especially calcium carbonate that is very abundant in these formations. We also have the subsequent formation of dolomite as a product of diagenesis, and these cycles can be seen here because at some depths we can have a carbonate which is very impermeable, and then immediately below that we have a section of the carbonate that is very porous and permeable. These are very good aquifers when they are deeper in the ground, and in fact they're the basis of several of the elements of the Edwards group, the Trinity group. One of the most prolific aquifers happens in a formation that is called Cow Creek here in Austin, and that formation is characterized by big bogular porosity. The differential dissolution is extreme, is a very good porous and permeable carbonate formation. And here is another exact transition between the impermeable rocks to the left and the porous and permeable rocks to the right. Here is another example of this variability of cycles, sedimentation cycles of carbonates, and how the upper layer exhibits almost no porosity and negligible permeability, but as we go down in the next cycle, then things improve considerably. So now we have porous and permeable rocks, very nice structure. And then when we go below that, just below that, again the rock becomes impermeable, as you can see there. And that's exactly what we try to understand when we look at well logs, is how is it possible to differentiate these good segments that have good porosity and good permeability. And again, we have to look at the conditions that will cause the different logs to respond differently. We have a contrast in porosity. Of course, the density log will see that. The resistivity log, compared to what we see above and below, will exhibit relatively low values of resistivity because of the increase of porosity. And then when we look at the effect of mud filtrate invasion on the resistivity logs, we will see differences between the shallow, medium, and deep resistivity. So it's important to remember these conditions, because that's how we have to look at well logs. And those are the kinds of things that we have to imagine when we see well logs. Rock composition, rock variability, the opening or not opening of porosity, the presence or not presence of permeability. Here is another close-up of the section of the carbonates with very good porosity, very good permeability, differential dissolution. It almost looks like a brecciated carbonate. And many of the hydrocarbon reservoirs and carbonates around the world, for instance in Mexico, have this brecciated pattern that gives rise to good storage and flow properties of hydrocarbons, of course also of aquifers. Very interesting structure. So when we look at these carbonate formations that have undergone differential dissolution, opening of pores, connectivity of pores, therefore permeability, one has to compare them against other rocks that are not as permeable. For instance, the ones that we see here at the base of this creek. But as we go along, we recognize that there's a lot of variability of pore structure, presence or not presence of fractures. So the interesting thing that one has to remember when looking at these rocks is, how do we see them with well logs? How do we sense them with well logs? And one of the things we obviously see is that because there's no potassium, uranium, or thorium in some of these formations, the gamma ray log will be flat as a pancake, despite the fact that we have a tremendous variability of pore sizes. Now, if one looks at the resistivity log, what's going to happen is this. At the bottom of this sequence, where things are impermeable, porosity is 0, then the resistivity log will exhibit very high values. Whereas as we go along here to these other rocks that have good porosity, then what we will see is that the resistivity log will decrease, largely because of the porosity. So compared to the resistivity log below, the difference will be extremely high. So very often what we look for in carbonate sedimentary sequences are places, cycles, rocks that exhibit low values of resistivity compared to the values above and below them. That's one thing. The second thing we look for is we look at the evidence of mud filtrate invasion. And how do we see that evidence? Well, we will see differences between the shallow, super shallow, and deep, medium resistivity logs, indicating that the rock percolates. So it's allowing mud filtrate to go inside and displace the original in-situ fluids. What about the density log? Well, the density log will show relatively low values of density, which means relatively high values of porosity. And what about the sonic log? Well, the sonic log will show that this rock, the one that is porous compared to the one that is below, will exhibit relatively longer travel times than the rock below. So the rock below is rigid, impermeable, so the time of flight is shorter than the time of flight through the rock that is porous and permeable here. Magnetic resonance will show that indeed we have pores, and will quantify the relative pore sizes that we have in this structure. And then if you run a borehole image log, be it ultrasonic based or resistivity based, we will also be able to see the texture of the rock. So we have various ways to ascertain the variability of rock properties, storage and flow, as indicated by the logs. Here we have another very close look at these porous and permeable cycles of carbonate sedimentary sequences. We can actually even see places where we have fossils, marine fossils. And all of this is a great indication of why these rocks have undergone accelerated dissolution, which causes the pore structure that we see here, the permeability, the pore connectivity that is very common and frequently encountered in these rock formations across the Texas Hill Country, which serve as aquifers all throughout. As an example of the intersection of a permeable rock with an impermeable rock that serves as pressure seal, here we have actually the outcropping of an aquifer. That above that we have an impermeable rock, below that we have an impermeable rock, but in between is porous and permeable, and then that's the one that holds the water. And here is outcropping the creek bed, and it shows the presence of water. It is also very common in the Texas Hill Country to find these types of karst features. These karst features are formed by the differential dissolution of the carbonates because of the action of water dissolving the carbonate and creating these pathways to the ground deep. And in fact, the Edwards Aquifer recharges a great deal from features like this that provide rainwater directly into the aquifer. So that's another very interesting feature of carbonate rocks, their ability to form these very prominent karst features that we see all around the Texas Hill Country. And by the way, what about the beautiful display of wildflowers in the Texas Hill Country right now? Look at this beautiful carpet. Isn't that gorgeous? Hello everybody, welcome to part 2 of the Carbonate trilogy. Today, part 2, it's going to be focused on storage and flow properties of carbonate rocks. Let's begin. The objectives, as I indicated in the first part, are the following. This presentation specifically is going to look at the unimodality, bimodality, trimodality, the multimodality of pore and throat size distributions of carbonates and how they affect their storage and fluid transport properties. Again, as I indicated in the first part, we have some ancillary lecture material that is described here. I hope you have a chance to go through some of the presentations, some of the pages, some of the elements of the compendium, so that you can expand the topics that I'm going to be covering here, especially so the chapters of the textbook. And here we have, perhaps it's important to begin reminding everybody what are the differences between the pore structure of clastic rocks and the pore structure of carbonate rocks. In clastic rocks, we have a very relatively simple description of the pore space because we have grains, and the grains have their shapes. We have sorting, distribution of grain sizes, and we also have their compaction and their cementation. And whereas in the case of carbonates, we have a significant variability of possibilities. We have interparticle, intraparticles. We also have microporosity. We also have moldic porosity. We also have skeletal porosity. It really depends on what is the original makeup of the rock and also how much diagenesis it was subject to. But we have indicated that there are a number of similarities, but there are also many differences that warrant a more specific description on the impact that these differences have on the petrophysical properties. And why not? Also on some of the physical properties, such as, for instance, electrical resistivity, magnetic resonance, we'll be talking about it, and other measurements. For instance, nowadays it's extremely popular to use dielectric measurements, frequency-dependent electrical conductivity and dielectric permittivity as a way to infer properties about this pore space. So all of these properties are going to vary significantly from one case to another, and also we're going to be able to extrapolate the parametric models for petrophysical or physical properties over a wider or narrower range of variability. Here's another three-dimensional description of clastic rocks. On the left, here we have a clastic rock, and here we have a carbonate. I want to make sure that you understand very clearly. I have said this many times, but it's important, at least from this sugar cube perspective, to see that the pore space in clastic rocks is what remains between the grain pack after you compact it, you cemented it, and so forth. But it's actually very relatively simple to describe that pore space. Whereas in the case of carbonate rocks, the space that remains is a little bit more heterogeneous and several concerns, including moldic porosity, for instance, the dissolution that we talked about before. So we have significant differences between the two. But let's look at this Fontainebleau sandstone sugar cube. What I have here, which is very interesting, is a histogram of the pore size distribution. Let me talk about this. Okay, so a histogram like this, like I'm showing in this section of the slide, what it shows is the pore radius, or the average pore radius in micrometers, and the distribution itself, it says how many of the pore spaces are contained within a given pore radius. And the area under the curve here, the area under the histogram, is the porosity of the rock, which in this case is 19.3%. Now, we can also, by mathematical means, do a streamlined approach to characterize the throat sizes. And the throat sizes are described on the lower diagram here, where the throat radius varies anywhere between 10 micrometers and 50 micrometers. So we have a histogram for the distribution of throat sizes and a histogram for the distribution of pore sizes. What I want to point out is that in most of the sandstone clastic rocks that we have, if you plot this histogram, it will tend to have a unimodal distribution. In fact, in many cases, it will look like a Gaussian distribution if you were to plot this pore radius or throat radius and a logarithmic scale, as is done here. So when you do that, so obviously the proper name is to say a log normal distribution. But that distribution actually tends to be very sharp. In other words, the standard deviation tends to be very, very small. Whereas if I were to do a grain pack like this, and I were to have, say, for instance, a layer or a laminated system, then you will see a bimodal distribution where one sector of the lamina will have small pore sizes and one sector will have large pore sizes. But when you don't have laminations like that, then most of the classic sedimentary sequences will exhibit a unimodal and somewhat sharp pore size and throat size distribution. Now, when we move to the case of limestones, and of course limestones or in general carbonates, they have a very wide distribution of situations. But let me show you this example of Mount Gambier limestone here. It's a very, very porous rock, 43% porosity, and we have a view of the solid composition right here, and then we have a view of the pore space, what remains in between the solids. But if you were to do the same plot in log of pore radius here on the x-axis and logarithm of pore throat radius here, you are going to find out that even though the distribution tends to be log normal in some way, what happens here is that the standard deviation has increased considerably more than for the case of the clastic rock. And this is precisely what we see in carbonate rocks. Or if you look at the throat size distribution here, it's obviously a biased distribution because one of the tails is longer than the other one. And that could be represented as the sum of two Gaussians or log normal distributions. So what we often see in carbonates, if you were to do this plot, is that you will display either a log normal distribution with a very large standard deviation compared to what you normally see in a classic sequence, or a bias distribution, which is a non-symmetric distribution, like we see here concerning the throat sizes, or we would see a bimodal or a trimodal distribution. That's what we typically see in carbonates. I want you to keep that picture in mind for the rest of this presentation. Let me show you another beautiful example of a Florida carbonate core, courtesy of Southwestern Research Institute. Here is a thin section, and of course you can see some of the relics of organic material or microorganisms, and also some of the intraparticle moldic parts of the rock. And then if we modify this scale and we show it at a distance here of 100 micrometers, here was 600 micrometers, so I'm going down in size. Let's see what happens, and then we begin to see two important aspects. We see now that we have a distribution of relatively sized large pores or medium-sized pore, but by and large what dominates over the rest of the rock is this distribution of relatively small pore sizes, which happen to be microporosity. Now, if you take 1 micrometer size here and you enlarge it, this is how it looks like. That's a microporosity. With these crystals are essentially recrystallized material. This example, there could be a number of cases, but we call it micrite. And the size is indicated here, 1 micrometer, is what is causing here is it's causing increased roughness on the surface of the pores. The pores are small, and there's a great deal of roughness to the point that the fabric, the so-called fabric, which is a measure of the surface to volume ratio of the pores, you will see that it's extremely rough because of this growth of crystals. But most of this porosity, we call it microporosity because most of the fluid that you have there is irreducible, in the sense that yes, we have porosity, the porosity is interconnected, but if you were to apply a pressure gradient, the fluids will not move here. They will tend to move on the larger pores. And so if you were to plot a pore size distribution of this rock, you will see here in a logarithmic scale that we have as again the histogram, we have three dominant modes. The one at the very end that I'm highlighting here with the cursor, that will be the microporosity. Then we have a small one, almost imperceptible peak here in the histogram that is called mesoporosity. And then finally we have the third mode of the distribution, which in this case is the macroporosity. So I want you to see that with this trimodality, essentially we have a complex pore network, and consequently the displacement of fluids here is going to be very non-conventional. Certainly not as simple as the one we would expect in a clastic rock. Now, if we go along, let me show you another example of moldic porosity. This photograph is courtesy of my friend Austin Boyd from Schlumberger. Here we have oolites and other marks of other, well, not others. Oolites are not living organisms, these are pellets. But we also have presence of some other, the casts of some living organisms. But what I want to show is that here we also have a multitude of pore sizes. In fact, if you were to do the same plot on a logarithmic scale of the pore size distribution as illustrated here, you are going to see that we have three dominant peaks, which is the micro pores, which in this case are invisible. All of that is taken by essentially irreducible fluid. And then we have the mesopores indicated here, and because of dissolution, and then we have the micropores that we have in these regions of space. So essentially we are looking at a trimodal distribution, and it's very important to see how the connectivity happens, whether the connectivity of the largest pores or we can assume that the largest pores have their own network of connectivity, or they have to connect through the mesopores. This is a very important concern when we try to quantify the fluid transport properties of this rock, because it's no longer a unique simple network of conduction of fluids as we had in the case of the clastic rocks. And here's another enhanced scale of the same rock. What I want to point out is that there are some regions on this thin section, the ones that are bordered with the blue, purple one, that are essentially covering micrometer, 100 or even 1000 micrometer size pores on average. And then we have another region here that has extremely small pore sizes, anywhere in the range of 10 to 100 micrometers. And then we have another region that has essentially microporosity, where the pore size on average is 1 micron. And so if you were to look at these values of corresponding permeability, you will see that the region that has microporosity will have an equivalent 1 millidarcy, whereas the largest pores we have an equivalent of 100 to 1000 millidarcies, and then in between you will go between 100 and 100 and 300 millidarcies. So essentially we are looking at a rock that has locally very large variations of permeability. And then it's important to know these, because when fluids are going to move through here, they will move with different efficiencies. One efficiency for the largest pores and throats, and one efficiency, lower obviously, for the smaller pores and throats, and the microporosity will just be irreducible fluid. So it's important to know that the genesis and diagenesis of these carbonates is very important, because they're going to control the pore fabric, the pore size distribution, or the throat size distribution. And I want to emphasize, I hope you keep this in mind, that microporosity is an ever-present petrophysical element of carbonate rocks, especially in particle and mud-dominated carbonates. If you remember the classification by Dunham and as expressed by Charlie Cairns, and also by Lucia. So those cases are critical for us to understand. And I'll talk more about the corresponding effects on electrical conductivity and permeability. So here's another very interesting photograph. In this case is also provided by my friend Austin Boyd. This is a rock that comes from the largest reservoir, hydrocarbon reservoir in the world, which is Gawar. I want you to see the 1-inch scale that you have here. And I want you to see just by simple inspection that we have a rock that, yes, it has relatively high porosity, but the curse of this rock is that the porosity is placed in groups of macropores, mesopores, and micropores. So we have a distribution that from the viewpoint of recovery, it will be very hard to mobilize the fluids at the same velocity in each one of the networks. So consequently, you are going to have differences in the velocity, the interstitial velocity of fluid here, where the velocity will be higher in the higher throat size, the largest pore sizes and throat sizes, and you will have almost zero mobility in the microporosity, and then maybe some in between mobility in the mesopores. It's very important. I want to make sure that you grab this concept, because when we characterize a rock by its porosity and permeability, let's say that we're only given those two parameters, just with those two, it's impossible to characterize the flow, for instance, when you have two immiscible fluids in the rock, because the movement, the front of the displacement of the fluids that are immiscible will have very, very interesting properties because of the variability of pore and throat sizes. That's something that is not described in the context of permeability and porosity. Also, when we have this distribution of pore sizes and throat sizes in a rock like this, we will have the so-called dispersivity because of the differences in interstitial velocity. Now let's look at another rock from the same reservoir. This is a waxstone. Obviously, just by simple visual inspection, we know that this rock has low porosity and low permeability. But in the context, in the grand context of pore size distributions, yes, we know that on average, the pore sizes and the throat sizes of this rock will be smaller than the previous rock, obviously. But in exchange, the pore size and throat size distribution here will tend to be a little bit more unimodal than in the previous case. And because of that, we will have a different phenomenon or a different functionality for the fluid transport in the rock. I also want to point out that different enhanced oil recovery methods will have to be applied to rocks with different pore size distributions or throat size distributions to favor or to somewhat balance, if you will, the differences in interstitial velocity that we have here. Second, when you have great variability on the pore sizes and throat sizes, obviously, even though the porosity, the total porosity is very high, then the recovery factor will tend to be low because of the discrepancies in interstitial mobility when this rock is subject to a pressure gradient that causes the fluids to begin to move. Whereas in a rock like this, we have a quasi-unimodal throat size distribution, and because of that, even though the fluid's interstitial velocity will be lower than in the previous rock on average, more of the pores will be displaced uniformly, and therefore perhaps the recovery factor will tend to be higher than in the previous case. Now, here is a plot, comparative plot of the two rocks. I call it the tale of two rocks, not a tale of two cities. But here is a thin section at the top of the rock that has 30 porosity units of porosity. The permeability is 97 millidarcies, whereas in the lower case, the sample number 2, the porosity is 18%, and the permeability is 2 millidarcies. Obviously, we have a big discrepancy. And when we look at the corresponding throat size distributions that are obtained from mercury intrusion capillary pressure measurements, we find, of course, that for the rock that has the largest throat sizes, we have a trimodal distribution where we have the micropores, the mesopores, and the macropores. And the ones that obviously contribute to the transport of fluids are the macropores and the mesopores. And the average size of the throats in this case is oscillates between, let's say, 2 micrometers and 8 or 7 micrometers, whereas in the case of the rock that has the lowest permeability, we see that we have a dominance by the microporosity. Much of the porosity is in the microporosity, and we have second part, which is the macro or mesoporosity, where we have a dominant peak. So this rock, as I said before, this is the second rock, obviously will have a more uniform displacement of fluids, even though it will be the interstitial velocity will be lower. Obviously the microporosity will not contribute to the transfer of the fluids. So here we have a tale of two rocks that have different porosities, different permeabilities, but to truly uniquely understand how the fluids are going to be transported to the rock, we need to know the pore size distribution and the throat size distribution beyond just porosity and just permeability. This is very, very important for understanding the differences between the two rocks. And why so? Well, I have to remind you that in the context of flow in pores, we have a very interesting relationship that we call the Hagen-Poiseuille equation, that essentially is the simplification of the Navier-Stokes equation in a capillary tube that has a straight cylindrical tube. The one thing that we know about this model, which is very important, is that when you apply all the conditions of Darcy's constitutive equations and also the diffusivity equation, then we immediately know what the permeability of this rock is as a function of the cross-section. The cross-section is very important, and the perimeter of the sample. So you see, the permeability, as opposed to the case of electrical conductivity, is a property that is highly dependent on the surface properties. Why so? Well, because the boundary condition that we have in this case is that we have zero flow velocity at the surface of the tube, and that boundary condition causes it's like a friction force that causes the velocity of flow, the interstitial velocity of flow, to be dominated or to be respondent sensitive to the surface properties of these fluids. So size matters, whereas in electrical conductivity we don't have, everything is volume dominated, then we will not have these surface forces, and because of that the properties will not depend on the size of the tubes, but they do depend in the case of permeability because of this very, very important condition that is surface forces. So keep that in mind, because when we have a distribution of capillary tubes, then obviously the interstitial velocity will be different because we have different cross sections and perimeters. So, and I know some people don't like this analogy, but I always make the case that a rock for many analogies is a very good comparison against a shower head. So when we have a rock, imagine that the shower head comprises all of the capillary tubes. If you sum the cross section here, it will give you an approximation of the porosity, but like in this shower head, all of the capillaries have the same dimensions, the same surface. So because of that, the interstitial flow, velocity flow through all of them will be the same, and that's actually a very good rock. The best rocks are always the ones that have the high porosity, and the porosity is in this case distributed in capillary tubes that have very large, first of all, they have a uniform cross-section, properties are the same, and that cross-section is large. That way the interstitial velocity will be the same across all the capillary tubes. Now, based on that property, and I want you to keep in mind this figure, because if you have a rock that has a unimodal distribution of throat sizes or pore sizes, then to predict the transfer properties of this rock is relatively simple. And I'm talking about not only predicting permeability, but also predicting some of these two-phase properties such as capillary pressure and relative permeability. But in the context of permeability, we have a number of equations such as the Cassini-Kármán equation, the Burke equation, the Timur, the Coates equation, the Timur-Coates, etc., etc. All of these equations are based on sizes. You will see that the permeability is always dominated not only by volume but also by sizes, an implicit parameter in the description of permeability that has to do with size, as opposed to what we often see in electrical conductivity. But what I want you to get out of these equations is that most of these equations make the implicit assumption that we have a dominant throat size in the distribution of pore sizes, throat sizes of the rock. But rocks are not like that. And so, again, please, profuse apologies, but let's look at rocks from the viewpoint of shower heads. Maybe some of you have a rock that looks like this upper right shower head that is barely dripping. It's almost like some of the openings here are clogged up, and so the flow is going through very few of these openings, and the openings are so small that the interstitial velocity is very small. Or you can go to this one where you have a uniform and large distribution, uniform and a distribution of equal, almost uniform throat sizes. Or you can go to what I call the eco-friendly shower head that has a distribution of throat sizes, and obviously what happens with this is that the interstitial velocity will be different across all of these, and consequently we will have differential behavior, dispersive fronts in the case of immiscible fluids, and all of those good things that we tend to describe. Of course, we also have super fancy showers like the one shown here, where we have also a very wide distribution of throat sizes. So what I want you to think is that, and this is a very good example, sorry, some people don't like to be invoking examples like this when we describe the complexity of rocks, but I just find it super easy to understand something complex like this when you have a very good simple analogy. And then the important thing is to always think about rocks that suppose that in this case all the shower heads have exactly the same porosity, that the sum of the cross sections are the same, but despite the fact that they have the same porosity, they don't have the same permeability. And also because when you have variability of throat sizes, then the efficiency of flow is not going to be the same. So keep that in mind, because this concept, this very analogy, is very peculiar to the case of carbonates. So in summary, and this is always what I say in some of the courses that I teach, that I always say porosity is overrated. Because why is it overrated? Well, because yes, it tells us how much of the pore space of a rock, of the volume of the rock, is occupied by fluids. But you don't know from just knowing the porosity how much of that fluid is in microporosity, macroporosity, or mesoporosity. And consequently, you don't know, if you apply a pressure gradient, how much of that volume of fluid is going to move. And you don't even know if the velocity, the interstitial velocity, is going to be uniform or not. That's the reason why it's very important not only to stay with porosity, but to reach the description of pore size distributions or even throat size distributions. Because those are the elements that we need to describe fluid transfer property, because this is very important based on the analogy of the Hagen-Poiseuille equation, is that many of these fluid transfer properties are dominated by surface forces. And surface forces are sensitive to size. So this is the important concept to take away. And here's an example of even more complex carbonate rock where we have fractures, we have matrix, we have bugs, we have microporosity, and therefore the question is, okay, so how is hydrocarbon or any other fluid, water, going to move through this? Well, what's going to happen is that the fluids are going to move, but they're going to move with different interstitial velocities. The movement will not be uniform, and some of the fluids, the recovery factors are going to be very small, despite the fact that the volume storage is high. So you see, typically what we want is a rock that has large storage, but also has large values of interstitial velocity and uniform values. That would be the best rock. But in rocks like this, we have the curse of nature because we have high porosity, but the interstitial velocity is not the same. And for the case of hydrocarbons, as illustrated here, we are going to have the differences in interstitial velocities is going to cause that some of the fluid that we have in the matrix is going to be left behind, and consequently the recovery factor will tend to be very low in a rock like this. And that's what we typically refer to as the efficiency of flow. And I just want you to do this diagram that is due to my colleague and friend David Herrick. Suppose that you have a rock that has 46% porosity. This is just for the sake of argument. But you have all the porosity in one single capillary tube. Then what's going to happen is that even if you have the boundary condition at the surface, well, all the fluid in this capillary will move with the same, well, approximately the same velocity flow. So you will have a beautiful shower head, maximum efficiency, because most of the fluid that you have in the rock will be mobilized as soon as you implement a pressure gradient. This is very similar to also what happens when you have electrical conduction. And let's say that this fluid is electrically conductive, so all of the fluid in the capillary tube will be electrically conductive, and therefore electrical conductivity will be enforced through every single part of this fluid equally. Whereas when you have a situation like this on the right, where you have pores and you have throats, then what's going to happen is that the electric lines or the streamlines, for the case of permeability, will no longer be straight, and then the concentrations of the streamlines will be high when you have small throats, and the concentration will decrease when you have a pore. And consequently, when you apply a pressure gradient, the consequence of this is that not all the fluid that you have present in the pores and the throats is going to be mobilized, is going to be transported when you apply a pressure gradient. This is exactly the same thing that happens with electrical conduction. So what happens here is that we do not have the same efficiency of transport, be it electrical conductivity or fluid transport, between the two cases, despite the fact that we have the same porosity. So it's very important to understand these differences, because once again, some of the properties, some of the physics, some of the phenomena that we're dealing with have a strong linking with surface forces, and surface forces depend on sizes. And here's another interesting plot that was put forward by Rothman in a landmark paper to show, for instance, that when you have a very complex distribution of pore sizes and throat sizes, and you apply, this could be electrical conductivity, or even if you apply a pressure gradient, the arrows that you see here are indicating the density of flow. So there are some sections of this rock, wherever you go, that have good density. But for instance, there are sections of the rock that, because of the way the rock is, or the intercommunication, if you will, when you apply a pressure gradient, there will be sections of this network that will not move at all, despite the fact that you have porosity. This is the critical point. You see, you have porosity, but not all the fluid in the pore space is going to move with the same efficiency when you apply a pressure gradient. In Arch's equation, this is the same thing for electrical conductivity. You apply voltage difference between the two ends, and then electrical current will move. But there will be parts of the pore space occupied by electrically conductive water that will not move, so the efficiency of the conduction will be lower. And that's actually what the M exponent in Arch's equation does. Because if all the fluid that we have in the rock, if all is, then essentially the volume of the fluid that is electrically conductive will be the porosity. But because of the way the pore space is being constructed, if you will, so when you apply an electrical voltage difference here, there will be portions like this that have fluid, electrically conductive fluid, but it will not contribute to the electrical conduction. And because of that, the M exponent will tend to be higher than 1. And of course, porosity is a number that oscillates between 0 and 1. And when you elevate that to an exponent that is larger than 1, then the value decreases, you see? So that exponent takes care of how much of the pore space is contributing to the conduction. And similarly for the case of permeability. Here are other paths of conduction or transport, and different sections of the rock are going to be immobilized of the fluid in the rock, and certain sections are not going to be mobilized. So essentially you have different modes of transporting the fluid in this example, and the efficiency of the transport is what I want to mention, because when you have variability of pore sizes and throat sizes, essentially what happens is that the efficiency of the transport decreases considerably, so that not all the fluid that you have in the rock is going to be transported regardless of how large a pressure gradient you apply. And here's an example drawn from an analogy with traffic flow. So this is a Google map picture somewhere in Mexico City. But what I want to point out is that you have some arteries and avenues that are very large, like this one, or maybe like this one, or maybe like this one. So if you apply a pressure gradient, so the interstitial velocity will be very high along these conduits. And look at what happens in the intermediate arteries here that have smaller throat sizes. Well, fluids are going to move there, but the interstitial velocity is not going to be the same. So we have if you were to capture the size of all these avenues and streets, well, that will be the porosity of the rock. But if you were to apply a pressure gradient because of this great variability of throat sizes, if you will, then the interstitial velocity will not be the same across all of these fronts. And because of that, the efficiency of the flow will not be the same. So essentially we have maximum efficiency when all the fluid that you have in the rock will move at the same interstitial velocity. But here is not the case. Or some of you that know Austin, Texas, and we know that Austin, Texas is a nightmare of traffic. It was not like that a long time ago when I did my master's in electrical engineering at the University of Texas. I'm talking about 83, 85. Man, we could go anywhere in a couple of minutes, even with bicycle, but now it's a nightmare. And so what happens is that you have all these streets that the interstitial velocity is very small, and of course at certain times of the day, even the large arteries like IH35 will be completely clogged up, interstitial velocity 0. But even though they have large conduits, sometimes the interstitial velocity is very small, or along MOPAC. But in times where there's not a whole lot of traffic, obviously the flow, the interstitial velocity along MOPAC or 35 will be much higher compared to the interstitial velocity that you have through Lamar or some of these streets, not only because they have traffic lights, but also because the size of those streets is smaller. So we have a distribution of the interstitial velocities of these fluids. So now, what I want to show you is I want to compare now the transport properties of clastic rocks versus the transport properties of carbonate rocks. So I have a couple of movies that I want you to see. These movies were captured with X-rays, and these were done by my PhD student, excellent student, very intelligent student, Colin Schroeder, has written several papers about this. So what I'm going to show you now is some material from him and some material from other experiments, but I will be very careful to give him credit about this. So what I want to show you with these movies is to exhibit for you in the clear graphical pictorial motion how the transport of fluids varies so much between clastic and carbonate rocks, so you keep this in mind for future work. But before we go into that direction, what we're going to do, the movies that we're going to be doing here are replicas of a process that we call mud filtrate invasion. And this process is very important because we have covered this idea before. In fact, we talked about this in the first part of the Carbonate trilogy. And what I showed there is that one of the easy and definite ways to assess whether a carbonate rock has permeability, it percolates, is by looking at the evidence of the percolation of the invasion on the electrical resistivity logs with different depths of investigation. And we do that why? Well, because when we have the process of invasion, let's say that you have a sequence of layers as shown here, and the electrical resistivity of those layers is like the blocky log that you have here. When we drill the well, fluids are going to enter the formations because we have overbalanced pressure. In other words, the pressure of the fluid in the borehole is larger than the pressure of the fluid in the formation. So because of the differences in pressure, fluids will begin to move into the permeable formations, but they will not move with the same interstitial velocity. So some layers, depending on the porosity and permeability, some layers, the movement, the transport of these fluids displacing the original fluids will be longer in radial distance than in others. And of course, this depends on whether this is early time or late time, and it also depends on permeability, depends on porosity, overbalanced pressures, a number of things. But what we do is we send logging tools. When we have this, we send logging tools such as the induction tool. It could be lateral log tool. And these tools have different radial depths of investigation. So when that happens, we have logs that sense the near borehole electrical resistivity, and we have logs that sense the deeper or virgin non-invaded part of the rock. And of course, for different situations, we look at one of the logs to do certain types of calculations and another log for another type of calculations. But definitely when we see discrepancies like these, those discrepancies in the case of water-based mud could be due to differences in salinity between the salt concentration in the mud filtrate and the salt concentration in the formation water. But they could also be due to differences in saturation. And saturation because the mud filtrate is displacing radially away the original in-situ fluid, and that displacement is going to give rise to invasion. So it happens because, once again, the rock is permeable. So that's what we see. So the experiments that I'm going to show you, and that's the reason why I'm talking about this, is there are mini invasion experiments. So we're going to do mini invasion experiments on pieces of rock. We're going to do one in clastic rocks so that you see what the consequences, and then we're going to do one on a heterogeneous carbonate so that you see the differences. So, and before we go there, just so that we know and put this in proper context, the part one of the trilogy, I talked about this example, which is on pages 13 to 15 of the compendium part 2. This is Smackover formation, and I was mentioning that one of the easy ways to recognize when you have a good segment of the carbonate formation is, first of all, that you have a slow rock based on the sonic log, and also that you have relatively low resistivities, relatively high porosities, and very importantly, that you have differences between the different resistivity logs with different radial lengths of investigation, because that is telling you that there has been invasion of the mud filtrate into the rock. And so that's the reason why we use the invasion as a very important quality control to determining whether a given section of a carbonate rock is permeable or not. So that's the important thing. Now, to do the so that you know how these movies were built, this is how they were done. So Colin Schroeder epoxied these cylindrical samples of rocks with a hole in the center, and the fluids were forced to flow in the center, and he imposed a pressure gradient between the fluids that went inside this hole and the outside of the rock. And I have to clarify that what he did is he dried out these samples so they are full of air, and then he was injecting either OBM, oil-based mud, or water-based mud. But what I'm going to show you today is water-based mud. And the size of the sample is 3 inches and by the outer diameter and 2 inches in height. And I'm going to show you 2 cases, one for Berea Sandstone and one for a spatially heterogeneous Edwards limestone. And this is a cross-section of the fixture that Colin uses, where, as I said, the center is hollow and the fluids are going to be moving through this section, and the fluids are going to be at higher pressure here than at the outer boundary. So consequently, there will be the motivation for the fluids to go from high pressure to low pressure according to Darcy's equation. And that's the size of the borehole, and that's the size of the core. We have the lower end caps and injection fittings. All of these has been hydraulically adapted so that it doesn't leak, and it's also durable, because the point is that Colin injected these fluids over time, and then at the same time that he was injecting the fluids, displacing the air, he was doing X-ray images in 3D of all of these, and that's how we can show you these movies that indicate how the fluids are displaced as a function of time. And so I'm going to show you 2 cases. One is a Berea sandstone with permeability 400 millidarcies and a porosity close to 20%. And these are a CT scan of the sample before fluids begin to flow. And here is a CT scan of the sample after a certain time the fluids begin to flow. And I want to point out the formation of the mud cake that we expect, because what Colin did is actually he replicated the conditions of invasion by injecting the fluid similar to what we have of mud, which as you know, mud is a combination of liquids, and then you have some solids in suspension, and when you force the solids in suspension to the throats of this permeable formation, then we have the formation of mud cake. And this is a plan view, and here we have a cross-sectional view, and we can also appreciate the formation of mud cake here. Now, for the case of the Edwards limestone, we're looking at a very heterogeneous rock. The upper left corner shows the CT image before invasion takes place, and then the lower right corner here shows in full color the distribution of fluids after invasion took place. And I'm going to show you, very interesting, if you compare this case with the previous one, here the displacement of fluids is very uniform. So we have a radius of invasion, we have a very nice beautiful front, but for the case of carbonates, that front is not truly a front, is some sort of a dispersed distribution of fluids, because the fluids obviously are going to flow with different interstitial velocities to different sections of the rock. But this rock itself, as I said, is an Edwards limestone. It has great variability in pore sizes and throat sizes, and so if you look at the section of the rock that has good porosity and good permeability, we're looking at about 24% porosity with a permeability of 2.1 millidarcies, whereas the relatively low or tighter part of this rock will have a porosity of close to 8% and 10 to the minus 2 millidarcies permeability. And I'm showing you the colors. The colors are the distribution of fluids in some transformative scale. But we also can see the formation of mud cake at the boundary. That's on the cross section. Okay. I also want to point out that Colin actually acquired samples of the mercury injection, mercury intrusion capillary pressure. And here is the capillary pressure curve, mercury saturation on the x-axis, mercury pressure on the y-axis for the Edwards limestone for two cases. One is a section that has good porosity, good permeability, that would be the blue one here, and the section that, the gray color one is a section that has the best porosity and permeability of the Edwards limestone, and the red one here, or orange, is the one that corresponds to the section of the Edwards limestone that has the poorer connectivity and porosity and permeability. And lastly, the one that you see here with blue, light blue, is the corresponding to the Berea sandstone. If you were to take this mercury intrusion capillary pressure and convert it over to the case of throat size distributions, what you're going to see is throat size distributions, first of all, for the Berea sandstones, showing a very, very sharp log normal distribution of throat sizes, very, very sharp, characteristic of, as I indicated before, of clastic rocks, where not even a Gaussian, this is like a sharp delta function. And the dominant throat size is about 8 micrometers, whereas in the case of the Edwards limestone, then you have a bimodal distribution where you have the mesopores and the micropores. So you have microporosity and you have mesoporosity, but obviously microporosity doesn't have fluids that are movable or marginally movable, whereas the mesopores are the ones that contain fluids that when you apply a pressure gradient, they are going to move. So please keep those in mind when we go and show you the movies. Okay, so just to show you the Berea sandstone, this is a plot of the quasi-homogeneous Berea sandstone, and then the porosity is 19%, the permeability is anywhere close to 400 millidarcies. And the sample was taken from a block, and this is just to show that the sample was taken almost parallel to the dimensions of the main layering of the sample. And here are the CT scans before the sample is subject to invasion. And this is similar to what we did to the carbonate rock, but I'll show you this in a minute. Here is the Edwards limestone. That's the way it looks. The porosity is 7-8%. Of course, we have variable permeability depending on what part of the rock you're looking at, as I indicated before, based on the mercury intrusion capillary pressure. And also, this image indicates how the samples were cut from the block of Edwards limestone. So with this, let's go to look at the movies. I'm going to first show you the movie for the Berea sandstone. Please look at carefully. You're going to see on one side of the movie, you're going to see how the fluids are beginning, how the mud is beginning to displace the air, and how this displacement appears to be almost piston-like in uniform as a function of time. And then you're going to have another image that shows how much fluid is being displaced as a function of time. And then we're going to do a similar plot for the case of the limestone. And we're going to see these cross sections as a function of time. In fact, the movie as a function of time, how the fluids are being displaced as a function of time, and you will see what the differences are between having a sharp unimodal log normal distribution of pore sizes, throat sizes, versus having a dispersed bimodal distribution of throat sizes and that you have in carbonate. So let's go to the movies now. Hello, so I hope you enjoy the movies. But the main point to take home, the most important element of information that you want to take away from those movies is that for the case of the invasion taking place in the homogeneous Berea sandstone, the invasion front, in other words, the water displacing air being the original fluid in the sample, the front is very uniform and the displacement is very, very homogeneous, the front. Whereas in the case of the carbonate sample, the front is patchy, is not uniform at all. You have glimpses of movement of fluid in the parts of the rock that are the most permeable, and then it's almost like it's moving effectively through those areas of the rock that have the highest porosity, the highest permeability, the highest interstitial velocity. It's patchy, very patchy. So let me show you in perhaps more detail what I just talked about here. So here is an enlarged three-dimensional view of that carbonate sample, this Edwards sample. Please look at all of these pore sizes, the variability. We have micro, meso, and macro porosity. And this is the inside view of the sample before invasion takes place. And then invasion takes place, and please pay attention to the way in which the fluid front is advancing and displacing the original air sample. Is first the larger pores are filled in, and there's a very specific pattern of how the fluids are moving into the rock, having more efficiency in those portions of the rock that have the largest pore sizes. Definitely not at all like the invasion front that we saw in the Berea sandstone or the clastic sequence. So please compare. This is the effect of having a bimodal or trimodal distribution of throat sizes compared to the very sharp unimodal distribution of throat sizes that we had in the Berea sandstone. And now let me show you in 3D. I hope this movie comes out well when done in YouTube. But please look at in all the detail the 3D sample, how this sample is so variable in space, and why there is actually preference of the fluids to go in the portion of the rock that has the highest interstitial velocity. Let me run this movie again. So here we go. Look at that particular sample over here that has the most important component of the high porosity and high permeability. So now, this is precisely what I wanted to drive home in this presentation with you, so that you understand the main principles of why understanding these pore size distributions, multimodal pore size and throat size distribution, has a very important defining influence on the transport of fluids within the rock. And here is a summary of what we saw. In the heterogeneous sample, we have the mud cake, of course, like we did for the Berea sandstone. But in the Berea sandstone, the displacement is extremely homogeneous, very defining, very conventional way in which the front moves away from the borehole wall into the end of the sample, and not at all compared to what we see in these heterogeneous Edwards limestone because of the variability in pore sizes. So why do we care about this? Well, we care because when we have a situation like a rock in Berea sandstone, well, that's very uncommon to have rocks like this. In fact, Berea sandstone is largely used for laboratory experiments because of their very unique homogeneous properties. But rocks especially carbonates, do not have these homogeneity. They have extreme variability in pore sizes and throat sizes. And because of that, we're never going to see the variability of displacement, the simplicity, if you will, of the displacement of two immiscible fronts that we saw in the Berea-Sanson, when in carbonates we have a more heterogeneous way in which the fluids are going to distribute to the sample. And please think about the effect of microporosity on this displacement, and please also think about the variability on the interstitial velocity of displacements, and please think about the recovery factor that we have in this sample. And there are samples of carbonates that are even more complex than the Edwards limestone. Here is a picture. I'm here photographed next to a block of stromatolite carbonate rocks. The stromatolite sample came from Italy, but I'm photographed here in Brazil. And the reason why this stromatolite sample is used in Brazil is because Brazil, in the deep water carbonates that they have in Campos or Santos Basin, is largely controlled by stromatolite fossil rocks like the one shown here, and the variability of pore sizes and throat sizes is incredible. The distribution of porosity, pore sizes, and throat sizes at any size of sample of rock will be prevalent, and because of that, the advancement of fluids is going to be extremely patchy, as is showed in the movies. And here's another interesting carbonate that by no means is comparable to Berea-Sanson, and this happens in the Permian Basin, where we have also large variability of petrophysical properties, where in fact when we see hydrocarbon in this area that I'm enclosing here, is because only in that portion of the rock we have good porosity and good permeability. The other sections of the rock, like the ones I'm showing here, they have very tight permeability, and some samples are fractured and some samples are extremely variable in their pore sizes, throat sizes. And when you have a rock like this, to produce a hydrocarbon that you have is extremely hard, so you have to use enhanced oil recovery techniques that can grapple with this very strong variability of pore sizes and throat sizes. And as I said, for the case of clastic rocks, very often one way to classify the clastic rocks is to do a plot of porosity on the x-axis and permeability in log 10 scale on the y-axis. And we know that a given class is one, a given class of rock is one in which the interstitial velocity is constant. And so that is the ratio of permeability over porosity. So if you take the ratio permeability over porosity, it turns out that this ratio is proportional to the interstitial velocity. So we know that a given class of rock will be one that has a constant interstitial velocity. This is also a so-called Leverett parameter. So we draw lines, these dashed lines, such that all the points along the dashed lines have the same K over porosity ratio. And this is typically the case in clastic rocks, where the decrease in porosity is due to the increase of cementation, keeping the aspect ratio of the pores constant. So there's a very defining way in which the porosity decreases for a given rock. And that defining way permits to classify all the rocks along this family of lines to be in the same class. This is a typical classification. That's the way we do classification of rocks and classifications of rocks, because of their storage and flow property in clastic sedimentary sequences. But this is not at all possible when you do this classification in carbonate rocks, because of the variability of pore sizes and throat sizes. And here's an example of a similar plot done for the case of carbonates. And these carbonates are done for the Hugoton field. I mentioned the Hugoton field, which is the largest gas field in North America, and the part one of the trilogy, of the carbonate trilogy. What I want to point out is that here, based on the various kinds of carbonate rocks that we have here, it is very, very hard to draw lines of common properties for the carbonates. Very, very hard because of these variability of throat sizes. So when you have dual bimodal distributions of porosity and permeability, the classification has to be done in a very, very different way. Certainly, if I draw an analogy with Archie's equation, one of the things that we saw in Archie's equation is that the m exponent, the porosity exponent in Archie's equation, can be, for a clastic rock, can be assumed to be very constant over a wide range of porosity. And this is very commonly the case when you're in the same class of rocks in a classic sedimentary sequence. And the reason being is that the way porosity decreases is because it maintains the aspect ratio of the pores and throats, and that's the reason for having that is because the way in which the packing and the cementing of the grains takes place in nature in a classic sequence is conducive to maintaining this relationship constant over a wide porosity range. And so that makes these kinds of correlations that are very constant for a wide range of porosity are possible because we have a unimodal distribution of pore sizes or throat sizes, which is not the case in a carbonate sequence. So, and the case that we have to take into account is that the interplay between storage and flow properties of rocks is extremely important. And I talked about the efficiency, how much of the pore space contributes to the connectivity to the permeability. And I talk about the pore throat constrictions, the tortuosity, and for instance, in this example, we have on the x-axis is porosity, maximum porosity, and this number being the y-axis is a measure of the efficiency of flow. When the number is 1, we have the maximum efficiency of flow, in this case for straight tubes. And the efficiency of flow tends to decrease regardless of the porosity when you have variability of throat sizes and pore sizes. And you also have increase of tortuosity. So these are the kinds of things that we have to take into account when we come up with some measure of the efficiency of flow, be it transport of fluids or be it electrical conductivity. And there are several authors that have taken to investigate this problem for the case of carbonates. I want to measure 3 papers for your reference. The first paper was published in the AAPG Bulletin February 2011 by Professor Eberly from University of Florida. And Professor Eberly and co-workers and graduate students have done a tremendous amount of very important work for the case of carbonates. And one of the things that they have found is if they plot the porosity and the formation factor similar to the plots that I was showing you, then it turns out that those lines are no longer similar to what I was showing you before, and the cementation factor tends to vary very non-linearly with respect to the variation of porosity, and to the point that there are several measures that need to be measures of the pore space that need to be taken into account to define the variability of the m porosity exponent in Archie's equation. And one of the things that is very important is that it's impossible to have the same m for a wide range of porosity. And typically when the aspect ratio of the variability of the pore sizes increases in the rock, then you can have, for the same porosity, different values of m exponent. And the value of the m exponent has to do with this efficiency or lack of efficiency of transport of fluids in the rocks. And here's another plot from the same paper where the authors plot is a perimeter over dominant pore size. This is the perimeter of the pore size of the dominant pore size. And then they conclude that based on this variability of pore sizes, there's also an expected variability of the M exponent. And one of the things that they find is that for typical grainstones, where you have only interparticle porosity, the M exponent tends to be very similar to what we often see in clastic rocks. But as soon as you have a bimodal distribution of pore sizes like in the rock at the top, then immediately the M exponent tends to increase to values of 3.45, 3, much higher than what we actually see in clastic rocks. And also the other thing that they find is that for very low values of porosity, it's also typical when you have this variability of pore sizes that the M exponent tends to increase very high. And that M exponent, what I want you to take into account is that the larger the value of M, that means that the least efficient the pore space is to conduct electricity through all the pore water that we have in the pore space. And this happens because of the bimodality, the variability of pore sizes and throat sizes than we have in the rock. So the more uniform the pore sizes and throat sizes are, then the lower the value of M. That means that the more efficient the rock is at conducting electrical current, or for that matter, at transporting fluids if you implement a pressure gradient. And similar, they have other plots such as porosity and permeability. What I want to point out is, I mentioned before that for clastic rocks, the ratio of K permeability over porosity is a very good way to define classes. But in this example, we can see that the classes are not very well defined, and also we see the colors of these points have to do with the cementation factor. And we can see colors everywhere, the difference being the variability of pore sizes and throat sizes. So I highly recommend you to take a look at this paper. It's a very good summary of the consequences of having bimodalities or differences in aspect ratio pores in carbonate rocks, and how these differences affect the efficiency of flow or efficiency of electrical current conductivity in rocks. And because of that, the value of the M exponent in carbonates very often could reach values of 3.5 and so forth, which is, as I said before, not very commonly seen in the clays of clastics. Here's another very interesting paper published not long ago by my former colleagues at Schlumberger Dahl Research, Raghu Ramamurthy, Ramakrishnan, T.S. Ramakrishnan, and some others. Ramakrishnan and Ramamurthy have been doing a very, very interesting work in carbonates to quantify their storage and flow properties in multiple ways, also to quantify their electrical properties. But this paper is very interesting because they attack the problem of carbonates with boggy porosity that at the same time they have microporosity. So this is like a dual porosity system. Evidently, if you were to plot the pore size distribution of these rocks, it will be bimodal or trimodal. And so what they do in this paper is that they explore this particular description of the pore space, and they come up with a way using effective medium theory to quantify the variability of the M exponent on account of the bimodality between microporosity and macroporosity due to boggy pore space. So this bimodality, what they do is they split the pore space into one modality, which is microporosity, and one other modality, which is the boggy space, and they quantify the relative concentrations of the two. They implement an effective medium theory, and as a consequence, they find what the M exponent will be as a function of porosity. And here what they have is are plots of the variability of the M exponent as a function of depth for many types of carbonates. And the consequence, of course, is that they have to be able to do that, they have to have a multitude of measurements, core data, and so forth. In the borehole, they have to have access to magnetic resonance data. I'm going to talk about that in due course in this trilogy. But that is the reason why the M exponent has to vary, because as you have bimodality or trimodality in the pore network of carbonates, then the efficiency of electrical conduction decreases significantly, and that's when the M exponent tends to increase. And so one way to attack this problem is to, from the get-go, describe these properties, be it the pore size distribution or the throat size distribution, as a bimodal curve. For instance, doing a distribution, a log normal distribution, or a superposition of two log normal distributions. And we tried to do this with, we actually did this with one of my former students, and we applied it to several carbonate samples with great success. It's not a trivial implementation, but it's something that can be done, especially because the cumulative function of this bimodal pore throat size distribution can be linked directly to the mercury intrusion capillary pressure. So one way to do these bimodalities or fit these bimodalities is that if you measure the mercury intrusion capillary pressure, that curve can be decomposed into two Gaussians, and when you do that decomposition of two Gaussians, and you can make the predictions for the weights of the two, the relative concentrations of the two Gaussians, and via this decomposition, one can better express the effective medium properties of the rocks, and also one can do better classification of the petrophysical classes. And more recently, with one of my postdocs, Zonhao's son, Ayaz Mehmani, and myself, we actually tackled this problem based or using microfluidics and also directly doing numerical simulations of electrical efficiency. We have not done this yet for permeability. We have started to do it, but the consequences are very similar. So here we designed networks, if you will, with unimodality or bimodality. And the idea is that if it's one unimodality, one can control the aperture of this distribution, standard deviation as a log normal curve, and we can design the corresponding network. And then with the network is designed based on this unimodality or bimodality, then we can apply numerical simulations to predict, for instance, what happens with the M exponent in Archie's equation. And lo and behold, we see the same behavior predicted by Ramakrishnan and Ramamurthy, or I should say Ramamurthy and Ramakrishnan, that the value of the M exponent will tend to increase when you have a unimodal distribution with a large standard deviation, or when you have a bimodal distribution of pore sizes. And then in this same paper, we tackle specifically the situation of bimodality by doing microfluidics. These are designing chips with specific patterns where one can design this bimodality and reconstruct bimodal trajectories, similar to the traffic problem that I was showing you as an analog for a situation where you have a bimodal distribution, that you have a section of the highway that is fast moving, high interstitial velocity, and you have another highway that has very low interstitial velocity, and the connectivity is different. Therefore, the efficiency with which they're sweeping, so to speak, the pore space when the pressure gradient or a voltage difference is implemented is different. So we have these patterns of bimodality, and what we find is, lo and behold, that the M exponent cannot be assumed constant over a wide range of porosity. In fact, what we have to do is we need to be able to quantify the differential bimodality in these carbonate samples, and from this differential bimodality one can re-estimate the M exponent to be able to calculate the or relate this to electrical resistivity. So a similar application can be performed for the case of permeability. And I also want to mention that Jerry Lucia at some point did his own classification based on what he called pore fabric. And pore fabric is a way of expressing more or less the roughness of the pores based on their genesis and diagenesis. But so he came up, Jerry Lucia came up with this transformation where he plots a so-called interparticle porosity on the x-axis and permeability. Both axes are in a log-log plot, and so he was able to define a fabric number, and based on the fabric number he was able to define the classes, because each one of the classes would have its own dominant interstitial velocity. But I have to say that this kind of classification of rocks only applies to carbonates that have a definite grainstone pattern. It does not apply to cases where you have buggy porosity. So not the extremes when you have microporosity, mesoporosity, and buggy porosity or macroporosity. It will not be applied to those cases which are much more complicated. And so as a way to conclude some of these concepts that I describe here, one of the most important things that we do in carbonate analysis is not only the analysis, this is the Hugoton field example that I described in part 1 of the carbonate trilogy, but what we have to do is to define the mineral concentration. This is very important because it turns out that the mineral composition of the rock has a very strong bearing with its permeability and when its fluid transport properties. So this is commonly what we do. We take into account all the logs, as many logs as we can. Sometimes it is actually necessary to use advanced logs such as spectroscopy logs to be able to define these mineral composition better, especially when you have more than 2 or 3 minerals. You need more data to define the concentrations of those 3 minerals. But it's very important because the composition will define the classes, as done in this example. And then second, based on core data, laboratory measurements of not only porosity and permeability, but also mercury intrusion, capillary pressure, it's very important to define these variability of throat sizes and pore sizes, to define presence or not presence of microporosity, so that we can define the efficiency of flow. And based on the efficiency of flow, once again, how much of the porosity, how much of the fluid, including porosity, is moved in unison with the same interstitial velocity when one applies a pressure gradient. That's a kind of definition for efficiency of flow that I want you to take away. So when we do that, then we have these classes, and the best class here is the red one, then the second class is the blue, the third class is the pink, and there's another class that is the maroon, and then the shell class. So this is one way to classify the efficiency of flow, and that's the holy grail, because not only this classification is based on the mineral composition, but it's also based on the flow properties, taking into account the unimodality or the bimodality of these pore size distributions. So when you do that, it's actually much more precise to recognize these classes and to understand the efficiency with which when you apply a pressure gradient to these for primary production or for enhanced oil recovery, how the fluids are going to differentially move through the rocks. And that concludes the presentation, but let me summarize the most important things that I said today. I hope that you got that the main, most important concept is that carbonate rocks exhibit great variability in the pore fabric. And I hope I was able to convince you that there are many carbonates out there in the world that have this bimodality or trimodality. Specifically, the presence of microporosity is very important, and the consequences that bimodality or trimodality in the pore throat size distributions have on the way in which the fluids are transported to the rock. This is very important. And please remember the movies and the examples that I showed between a clastic rock, which tends to have a unimodal pore and throat size distribution, and a carbonate rock that has a bimodality and trimodality, and how the efficiency of flow is going to vary greatly because of the partitioning of the pore space in these modes of transport that we have. One of the things that I didn't mention here, but it's very important to have in the summary, is that carbonate rocks also tend to have mixed wettability, oil wet and water wet. And this also can have significant effects on the transport properties, especially when you have immiscible fluids going, 2 or 3 immiscible fluids going through the pore space. I also mentioned the important thing that carbonates tend to have also, some carbonates tend to have very high porosity, high permeability, but it's not only important to define the porosity and permeability, it's very important to define the partitioning of the porosity and permeability of the pore space so that we can understand the differential ways in which the interstitial velocity will cause this shower head, if you will, to behave differently when we apply a pressure gradient. And what I want you to take into account is this concept of efficiency of flow, how much of the pore space is being transported when we apply a pressure gradient. A similar concept was implemented and considered for the case of electrical conductivity, and I show you a few examples at the very end with the papers that I reference, that the M exponent in Arch's equation tends to be very high, 3.5 sometimes, for the cases where you have extreme bimodality in carbonates, because that means when M increases, what this means is that the efficiency of conduction decreases considerably. And the other thing that I want to say is that it's very important to try to define classes of rocks with the most complex models of bimodality or trimodality of pores and throat size distributions that you have. I also mentioned that for all the parametric models that we often use for clastic rocks, in which we try to predict permeability for a wide range of porosity and maintaining the parameters of the models constant, that can be done for the case of unimodal distributions of pore sizes and throat sizes, but definitely those parametric models do not work very well. They're not accurate, they're not reliable when you have bimodal or trimodal distributions of throat sizes. And please, I have a few review questions. It's essentially driving into the most important concepts that I described in this presentation. I'm just letting this slide stay here for a few moments so that you can read it. These are some of the questions, and then I have a second set of questions also having to do with microporosity, the effect on electrical resistivity, the dispersivity or not dispersivity of fluid front space on the differences in interstitial velocity, the influence of this variability for early or late time behavior of the transport of fluids, sweep efficiency, essentially the efficiency of these systems to either conduct electricity or transport fluids, and the usage of mercury intrusion capillary pressure as a way to define the distribution of throat and pore sizes. So I hope you liked the presentation. I really want to thank a few people who helped me with some of the elements of this presentation. First and foremost, I want to thank my PhD student Colin Schroeder. I used a lot of slides from his work, and I thank him profusely because his work is excellent is opening up new ways of dealing with carbonates, and his X-ray movies and analysis are certainly a step forward into the proper understanding of storage and fluid transport properties of carbonates. I also want to thank Charlie Cairns, Jerry Lucia, and Peter Hennings for allowing me to use some of their material. The same thing with my former colleague Austin Boyd, friends David Kennedy and David Herrick, and by all means the material provided by Baker Hughes and Schlumberger with their permission that has significantly enriched this presentation. With that said, I want to thank you. I hope you enjoyed the presentation. I hope you like it. I hope you have a new pair of eyes to see how carbonates have a completely different way to transport and store fluids in them compared to the case of clastic rocks. And I hope that you understand that some of these parameterizations and studies are frontier work, and we hope that more researchers get into studying these carbonates. They're very important not only for hydrocarbon reservoirs. They're very important for geothermal reservoirs, for water aquifers, for soil remediation, for many situations. So understanding this efficiency of flow is very important. So I hope you like it. I hope you like the movies, and hopefully we're ready to go for the third part of this carbonate trilogy. So until then, please follow me, ask me questions, and if you have any suggestions for improvement, don't hesitate to contact me. Thank you, and hook 'em horns.